All right, time for another DraftPhysics.com, DebatePhysics.com. Videos, presentation. Yeah. So anyway, kind of under the weather. Some sort of health issues. Who knows? Vague, kind of weird symptoms. But anyway, just life is so much fun. Anyway, so I'll try to endeavor to persevere here. And icansciencethat has made some sort of video. It's titled "Why is Work?" ? And then it says "What is work?" on the video, but whatever. He's not going to go anywhere near the subject, I'm sure. And this is with the context of sort of being badgered to explain how heat isn't work. And that if you're going to pull all the energy out of something, okay, take away its energy. And the Joule principle is that you can do that in such a way as all of the work, all of the energy, is in the form of heat, eventually, inevitably. And, so these are real arguments, and so it goes back to the whole idea of what is friction. And friction is the application of a force, gravity, in the case of most of these demonstrations. And it's a time-dependent force, and the amount of force you have to overcome is completely dependent on how long you're in the force. And he's just going to totally ignore that argument and just preach, the sermon about the Holy Ghost energy. At least that's what it appears. I just jumped in a little bit, and he's just doing sliding block crap. The standard this isn't really physics. It just really isn't. Anyway, I think I can hit the button.
Welcome back to icansciencethat. Let's continue our discussion of work. What exactly?
So it's not really going to be a continuation of the discussion, because the discussion was about the definitions you have for this energy that you produce. This 1/2 mv squared, the 25 times the fuel to go 5 times as fast, or the idea that if you're going 5 times as fast, you can do 25 times the work. Now, it never happens anywhere, and that's the problem you have to articulate a solution to. And he just isn't going to go anywhere near doing that.
Is work, and how does that relate to the concept of momentum? We found this definition for work, and let's talk now a little bit about why it should be that, and maybe whether we should consider something different.
Considering something different is just, it's physics, and it really should be right. And that's all you're really saying is the current 350-year-old nonsense accurate or inaccurate?
So, work. What is it? What does it mean to do work? Let's imagine our job is to move a crate to the other side of the cargo bay.
Really? There are Klingons
Oh, I just hate cartoons.
on the other side of the hull, and this is our job? You son of a...
Moving a crate, what does that take? It's going to take force. We're going to have to push on the crate. And if we push really hard, is that doing work?
Yes. It's the obvious answer. So again, the what you always have to say is well, where does the energy go? You're applying a force. Where does the force go? And the simple argument is it can be absorbed and something will take the force, or it can be reflected, or it can be a combination of those things. And the fact is that if you push on something and then you look at it with a camera that can do the heat signature thing, you'll probably see that you made some of that, that pushing wasn't all no work, because you left a heat signature behind. That was work. That is energy. It absorbed momentum and converted into little things moving.
Or does it only count if we're able to move the crate? What if it's a really heavy crate and I push on it and it doesn't move, right? If it doesn't move at all, I'm still working hard. I'm still working up a sweat here. Am I doing any work?
All right, so this is, again, holding something up against gravity. It's just a silly physics definition to say you're not doing work because the only reason why the thing is staying where it is because you're applying a counterforce to the gravity. So clearly, if you're making a force, a counterforce, you have to be doing work to be making that force. You can't make a force and do no work. That's free force or free energy. So you're obviously working. I mean, this is just so trivially nonsensical that physicists will defend this idiotic notion that the only work you can do is to move something linearly, and that there's no other way the energy can be dissipated into the environment, when, of course, it can be dissipated into the environment all kinds of ways.
Even if I push 10 times as hard, if I'm not able to get the crate to move, I think the foreman is going to say that I didn't get the job done, right?
Yeah, so this isn't about strictly speaking, the definition isn't about getting a job done. It's about collecting a force. It's about transferring it from one object to another. That's what work is. You transfer the energy of your horse into the movement of the boulder or whatever it is. But it's a transfer, and you can just talk about how some transfers are efficient and some aren't so efficient. But this is just silly to say you didn't do any work.
And that's not getting the job done. And even though I'm sweating up a storm, if the object is not moving, I'm not actually accomplishing any work. So,
so even though their own theory says so Professor Lewin will tell you that you can hit a little piece of metal into a big giant piece of metal, and the fact is that twice the energy goes into the twice the momentum goes into the big object, even though it doesn't move. So even though there's no velocity, it's there nonetheless in some magical form.
Job is to move the crate. I have to move the crate to do some work. I think that's a reasonable...
I think it's just a silly standard, because we know that there's all kinds of reasons why the crate isn't moving, because you're pushing on it, you're stressing a bunch of little fibers and different things, so all of those things are all stressed. If it was glued to the floor, you could understand that. If you're pushing on it, the glue could be stretching and doing all kinds of things, and just like a rubber band could be getting hot, and so it's just a silly definition to say this is something about how far you move something is the definition of energy. I mean, it's just not a good definition. All right, should be back in such
perspective. So no matter how hard you push, if you didn't move the crate, you did not do work. And that means force cannot be work. We cannot say that force is work, because you could push really hard on something and have it not move.
All right, so this is just sort of breaks the whole conservation of energy kind of argument that, you can always find the energy somewhere. You apply it, it has to go somewhere. Even Richard Feynman's pretty explicit about that. So, obviously the work is getting transferred into the ground. If the adhesion is very good, then you're pushing on the ground. I mean, those are always the deductions, but clearly you're pushing on the ground through the force of friction, so there's going to likely be a lot of motion that you can't see. Fact.
Right? And if it doesn't move, we didn't accomplish anything. That can't be work. Let's take another look at this sliding friction example, where we have matching masses.
Right, so we went over this, and the whole argument is that you have an obligation to prove that there's 4 times the energy in the ground. That the object had 4 times the energy, and you collected it somewhere and said, okay, here's 4 times the energy. We conserved the kinetic energy. So you're supposed to show me that happens. I'm arguing there's only twice it, because there's only twice the gravity, so there can only be twice the energy, because it only overcame twice the friction. So there's only twice the energy in the ground. And, you're not coming anywhere near the subject. You're just pretending that this crap says all you need to say, and it doesn't come close to saying what needs to be said, or proving what needs to be proven.
But we launched them with different speeds. And what we had said is that the yellow object goes 4 times as far as the blue object. That was the experiment we've kind of been talking about. in this context of doing work by moving an object, I think we ought to agree that if our job was to move the object 4 meters, in the case of the blue...
It says you. So again, no, the object is to prove the physics theory. Your theory is that it moved 4 times the distance because it had 4 times the energy. My theory is that it's like thin ice. I mean, like pushing something on ice versus pushing something on gravel. That all you've done by increasing the velocity is change the amount of friction per inch on the surface, and so there's a lot less friction, a lot less transfer of the energy. So again, this isn't, to have to go through this minutia of all this verbiage to get you to concentrate on the real point. Is there 1 unit of friction here, and is there 1 unit here, 1 unit here, 1 unit here, and 1 unit here? That's what you have to demonstrate, that the friction is the same regardless of velocity, and that you created the same heat in the surface regardless of velocity. So you're not coming anywhere close to the where the crux of the argument.
Object, we have not done the job. How much of the job have we done? Have we done half the job? I think it's pretty clear we have not. If we want to move the blue object to the 4 meters that the yellow object has gone, we're going to have to do it 3 more times.
So again, yes, 3 more times at the slow velocity. So again, just ignore the subject entirely. The argument is the blue one has a lot more friction, and that this experiment has the same friction as this last mile that this one travels. So the last quarter of the trip for this one is the same as this experiment in its whole entirety. And the whole argument is what happened over this 1 second. This half the time here over this huge amount of surface indicates that, yes, it was a lot less force per inch on that surface. 1/3 the force on that surface. 1/3 the friction. Because it's 3 times the distance in the same 1 unit of friction. You're just ignoring it. I mean, this is just why the world sucks. I mean, you can't get people to stay on subjects. These are scientists, and they can't stay on subjects. I mean, it's just pitiful.
We've only done 1/4 of the total job. And so by that logic, 4 times...
That's not logic. I'm sorry, okay? There's no logic here because we all know that there's efficiencies to increasing velocity. And those efficiencies work for rockets going into space. If they take their time to get into space, they'll use about 1 million times more fuel. So the whole objective is to get up to a very high velocity very quickly, to escape the gravity, to escape its influence, to prevent it from making you do more work. Less time in the stream, you get pushed down the stream less distance. I mean, these are such obvious arguments, and you're just evading every single one of them. And it's really bad on you. I mean, what, you think nobody in the future is going to be smart enough to figure out that you just evaded the entire subject?
Times the distance is 4 times the work. So maybe distance is the work. Maybe that's what it's all about, right? If all my job is to move this crate from one spot to another, then maybe how hard I work has nothing to do with it. It's just about the distance.
Don't worry about it. Get to work. These crates aren't going to stack themselves.
I mean, who needs this crap? It's really disgusting. Like, again, these are supposed to be intelligent people. This is how they have their intelligent conversation. Look at this is my favorite TV show. Badly drawn cartoon man.
Let's consider, what if I want to move these 3 blocks, my 4 meters? If I just do one of them, then I've done 1/3 of the total job.
Again, just evade the subject.
I can do it 2 more times to get the job done. This is the equivalent of moving a 1 kilogram block.
No, it's nowhere near equivalent because it's exactly the same amount of energy in each circumstance because you're not changing. The first one doesn't go slower, the second one doesn't go faster, and the next one doesn't go faster. So again, it's just just evade the subject entirely.
Over 3 times the distance. Right? I've done 3 times the job by going 3 times the distance.
And right, if you would have done it by increasing the velocity by 3, you would have gotten 9 times the distance. You would have made a huge advantage. You would have gotten even more distance. So the power of velocity is clear. Velocity will get you more distance because velocity defeats gravity. Velocity defeats any force you're having to deal with. So whether it's a stream or whether it's paint spray or whether it's raindrops, the faster you can get out of the rain, the less wet you're going to be. That's how it all works. That's the argument, and your obligation is to prove this works somehow in some different way. And you're not going anywhere close to that. You're just saying, believe me when I do this, smoke and mirror bullshit, when I change the subject.
I just did it on 3 separate objects. Consider instead, let's combine it into one big object. So we're going to do one big object, and the job now is to move that object over my 4 meters of distance. Wouldn't that be fair to say that that's the same amount of work as if I had moved it as 3 individual blocks?
No, because you're not accounting for the fact that the surface area of your friction has now increased dramatically. You don't have 3 surfaces, so you didn't even do your blocks in the right condition, so there would be the same amount of friction. So obviously you've changed the experiment.
How much work was that, right? Let's see, how much work was it? In our previous example, we had worked out that...
I mean, not to concede that friction is about surfaces and surface areas. Kind of silly.
We were looking at half a Newton of force from friction in that example. So let's stick with that.
So why? Why? That's your assumption. You have no evidence of how much friction there is. You have no evidence of how much heat goes into the ground. You have absolutely nothing. You're just telling us this is our theory. Believe it, or else we'll insult you.
And friction is a topic we really haven't delved into. I'm not planning to delve into it in this video. Maybe in a future video we can talk more about it.
Oh, whatever. Yeah.
But the simple version is to say that if we were...
So the whole argument about the other 2 videos was the subject of friction. That's the whole subject. The whole subject is friction is what the block is working on. That's the thing it's doing work to, is the ground and its own surface. That's the work. And your obligation is to show that 4 times the distance is 4 times the work by showing us 4 times the heat in the surface.
Seeing half a Newton of friction from the block, then pushing with anything less than half a Newton will simply not move it. The friction will stop the block. If I can't push with half a Newton, I can't move the thing. So I'm going to be trying to push with the minimum possible force to get the block to go across to the other side.
So this gets into static friction, all kinds of other arguments. That's not really hard science, frankly, and doesn't have anything to do with the subject, again. The subject was you have the objects already moving. They're going to hit the surface now and be sliding across the surface with a known velocity.
And maybe we'll talk about friction in some future video. If anybody's interested, give me a shout. Maybe we'll go there. For now, I'm going to apply my half a Newton until I get the block to the other side of the room, and then I'm going to stop pushing. And friction will bring the object to a stop. Okay.
No. Half a Newton what? A constant half a Newton? What's, again, this idea that human beings can create a constant force is a silly proposition. How do you create a constant force on the block? Because the faster you go, the faster you have to go, so to speak. And it has to be completely proportional to the speed it's going. You have to keep just adding 5 miles an hour. So it's going 10 miles an hour, you have to make it go 15, so you have to add 5. It has to always be the same amount of extra. Almost, I'd say it's impossible for a human being to do that.
Sweet. So let's do it again with our 3-block combo. I'm going to do 3 at a time. If it took half a Newton to move 1 block, again, without going into how friction works.
Not going into the fact that friction is a surface contact and it's per square inch and all that kind of stuff, and we're just going to pretend that stacking these blocks is going to be the same as having them end to end, when, of course, it won't be.
The way if we model friction, it's going to take 3 times as much force.
Right, the way you model friction. You don't show it, you don't prove it, you don't do any experiments, you just state it. This is our model. And it's not right, it isn't the truth. And that's the argument. And your counter argument is, shut up, we don't care that you think we're wrong. Yeah, it doesn't matter. You're not relevant to our religion.
To move a stack of 3 blocks. And I think that's pretty reasonable to expect. So let's compare what would be the difference between moving individual blocks across the room or moving this stack of 3.
So again, let's just understand. They think a spring compressed twice as much is 4 times the energy. So you put one mass on top of the scale, and it weighs 1 mass, and then you pick up another one, put it on a scale, and it weighs 2 mass. They say that's 4 times the energy. Well, how did I get 4 times the energy? Both jobs were exactly the same. I did the same work on this side that I did on this side. How could that possibly be rational?
If we did the blocks as individuals, each block took us half a newton to move it, and we pushed for 4 meters. But we did it 3
All right,
total
so
times.
nothing tested, no experiments, just talk. And that's all you get out of these people. Their silly theory, their statements. This is what happens. 25 times the fuel to go 5 times as fast. No proof.
And we multiply that out, we get 6 newton meters of work done. If we push the stack of blocks all at once, we said it took 3 times as much force, but we only had to move it over 4 meters. But again, you'll notice that's the exact 6 newton meters of work. So what have we decided? I think we've decided that based on this context of what it means to accomplish work, how hard we push on the object is part of the answer. And the other part of the answer is how far we manage to make it move.
All right, so he's going to keep doing it. We know the only place the energy goes is into the ground. The friction, the movement of the particles on the surfaces is where the energy went. All the linear motion was converted into the movement of little objects. It has nothing to do with anything called distance, and again, ice proves it. I can make something go further and further and further. Just make the ice slipperier and slipperier and slipperier. Put a little bit of coat of water on it, and I can take the same energy and I can go 10 times the distance. So again, this argument that has something to do with distance is absolute crap. This is so bad that he won't respond to the real subject. He'll just do this instead, and then he'll insult my intelligence. He'll say, I don't know what I'm talking about. Oh, fuck you. Yeah.
How about if I push the object even harder? If I push the object harder, I could get that thing going faster. I could move it across the room much quicker. Would that count as more work? I think we could make the case that that's certainly seems like more effort, but
Oh, I mean, it's more effort, but effort isn't work. This is so mushy shit.
we didn't get any more work done. We just got the work done faster. And as valuable as that might be, that's not more work. It's just faster.
All right, so there's no way to push the block faster and not get more distance. So again, that's just silly. So I don't even understand what he just said. Distance is the work, so obviously it's going to be more work. I don't know. It's just ridiculous.
Work. And based on that statement, I think it's fair to say that we should not be including time as part of our work formula.
Right, we shouldn't. It's a time-dependent force. So a stream flowing down the river, time-dependent force. A certain amount of river goes past a point in a certain amount of time. Paint spray, a certain amount of paint spray comes out of the paint sprayer in this much distance, and that's the force. That's what the capacity of it is. Wind, sandblaster. It doesn't matter what example you use, and it's perfectly, all of those experiments will do exactly the same thing gravity does. So it's just silly to say gravity isn't the same kind of mechanism. That there's a certain amount of gravity goes through an area in a certain amount of time. And that's what you're collecting, is the impact force of that gravitational capacity. Leonard Susskind teaches it as water flowing. I mean, So this nonsense that this friction being pushed into the surface, okay, isn't a time-dependent force, that you do not collect it in units of time, is just so dishonest.
The work formula is going to come from the amount of force that we applied, and it's also going to come from how far we moved the object.
All right, so it's really just going to be about the friction. That's the stopping force. That's the force, not the force, but that's the mechanism collecting the energy. And again, you reduce the friction, you put, ice versus gravel. You get a whole bunch more distance with the same experiment, same experimental evidence, same experimental impact energy in the experiment. You get gigantically different results based on the friction you create. So this is about the friction, nothing else. If you threw these things in space, they're only going to go twice the velocity will be twice the distance. Okay, it's not going to be 4 times the distance. So we know this is about friction and how it pulls the energy out of an object.
So that brings us to this. Work is just force times distance. In our formal equation that we started with, we also had an extra term on there with the cosine of theta.
Yeah, well, look, who cares about the tangential, components in the same direction? So again, that doesn't have anything to do with this problem of proving your model is accurate. Proving that your 25 times the fuel to go 5 times fast model is accurate. 5 times as fast means 25 times the work done. Yeah. No, it doesn't.
So what is that about? And that little cosine theta there is a nod, if you will, to the idea that not all of the force that we used was actually accomplishing anything, right? Maybe some of the force was sort of wasted in our efforts.
All right, so I don't even know why he's saying that. It just has to do with the direction. If you got the direction pretty straight, then this cosine theta doesn't have anything to do with anything other than angles at which you're applying the force. It doesn't have to do with waste.
Like if you push on something really hard and it does not move at all, you're not accomplishing any work. That's in here with this distance.
Oh, brother. So he said this already 3 times, and obviously you're still... Work is heat. I mean, you buy heaters. What do you think what do you think the electricity is doing? It's making heat. That's the whole idea of the damn thing. So obviously the heat is work.
But what if I apply a force and kind of like an angle? I'm like pushing the crate kind of down while I'm also pushing it. Then I'm going to do extra force. I'm going to put in extra effort. But that extra force doesn't contribute to the job.
I don't know if it's actually extra, but whatever. I mean, you could have the same force at this vector, 7 newtons, or you could have 7 newtons this way and 4 newtons that way. So, didn't make that clear.
That I'm accomplishing it. So, this force here that we're saying is the force that sort of causes the movement. This is the amount of the force that's contributing to the movement of the object.
All right, whatever. So again, just baby talk. This has nothing to do with reality. This has nothing to do with dealing with a rational understanding of conservation of energy. This is just so bad. That this guy graduated from some college with a physics degree, and he's teaching physics, and he's he's saying silly things like, well, what does friction have to do with it? Yeah. If we move a block, we must give the same momentum. Whatever that means. The same relative to what?
So that's the physics definition of the word work, and what I hope is a pretty good intuitive explanation of...
Oh, fuck you. Just intuitive. What's intuitive? What a pile of nonsense. I make the surface slicker, I make more energy. It goes much further when the ice is slipperier. So, therefore, I made free energy. It's not the fact that the ice is taking less of the energy away from the object. No, that can't be the truth. It's just too ridiculous. So bad.
What it means and why it is the way it is. And why we don't just use momentum as work. But let's consider momentum. momentum.
So he thinks he can prove anything about these two subjects without actually analyzing the product. What was the product of the experiment? And you didn't do anything. You didn't provide any evidence that there's 4 times the heat in the surface. None. That 4 times the work was done. That if we put it in a joule tank, it would be 4 times the heat. You didn't show that there's any reason to believe that at all. It's not intuitive at all. I push it in space, it goes twice the distance in the same time. Twice the velocity, twice the distance. Your whole formulation collapses.
And the conservation of momentum seems to be pretty fundamental to the universe that we live in. I think we can agree that momentum is conserved. Perhaps we can agree that momentum is conserved in all cases. Certainly, what we normally would say is...
Yeah. Again, there's no point in agreeing if you're saying there's 4 times the heat in the ground, because that's not the same momentum. I mean, if you're saying the thing knocks down twice the bowling pins, it can't have the same momentum. It can't conserve the momentum. This is so fucking irritating.
Is that momentum is observed in a closed system in which no net force is acting. What do I mean by that? Another way to say that might be to say that a force, what we call a force, is when momentum is being transferred from one object to another. If momentum is exchanged...
Right, so gravity is a force, it's exchanging momentum, and it's clearly doing it in units of time.
Between objects, the way that exchange is going down is what we call force. Force is a measure of how much the momentum is being exchanged between objects in the system.
So that's just silly. Obviously the force is the momentum. It's not how much is being exchanged, it's how much is there. And you either exchange it or you don't. Oh man, it's just so bad. Force is the quantity of motion. Force isn't a transferring medium.
So what is a net force then? A force acting outside the system is just a force that we're not considering that object. Whereas that object that is providing that momentum is not part of our system. It's not.
So again, what sense does it make? Oh, the force isn't part of the system. Yeah, the thing with the momentum that's going to exchange the momentum isn't part of the system. Whatever that could possibly mean.
Not what we're considering. Not what we're talking about right now.
Right. The bus that's going to hit the Volkswagen isn't part of the experiment.
Okay. So, for example, let's say I'm going to push on the crate. And I get the crate going. I push it and it accelerates. In order to do that, I have to apply a net force to it. And that means I'm going to be transferring some momentum to it from outside the system. If I widen my system...
Yeah, so is it a net force or a constant force? You're not making any sense. Why don't you go back to the spring example? There's a certain amount of compression in the spring. It's a net amount of energy. There's not any more energy. There's just what's in the spring. I mean, you really have to make sure you're not, fudging around with these different concepts. Clearly, gravity's a constant force.
System a little bit, I will see that where I have transferred the momentum from is the ground. I have to push against the ground in order to...
So too silly. I transferred it from the ground. Sorry, the ground is... You're doing work on the ground. You're bugging the ground. You're imposing your collision on the ground. The ground isn't doing the work. You are going to do the work. You're going to be the expanding spring, moron. Oh, this is just so silly. I mean, I compress a spring against the wall. He's saying the wall is providing the energy. I didn't provide it by pushing the spring. No, the wall provided it.
Push with an equal force on the crate. I will transfer momentum into the crate. And the exact amount of momentum must be balanced to keep the conservation of momentum. The way that balance goes is into the ground that I'm pushing on.
So it's just too ridiculous. If the wall moves, if it has momentum, then the thing isn't going to leave with the same velocity. So we're back to put the spring between 2 heavy masses, put the spring between 2 light masses, and you'll find out that you get different amounts of momentum out of the spring. So the spring isn't very reliable, is the obvious conclusion in giving back all of its energy. But if you really try to get it all, then, twice the velocity is going to be twice the work.
Right? And because the ground I'm pushing on has a tremendous mass, we're not going to see any measurable velocity there. But the rule of conservation...
So again, he's saying it's there even though it's not there. So that's the joke. So again, their theory is if I have two blocks, okay, one mass, and a spring between them, and I launch them, and I get a velocity for each block, will it be the same? He's saying it'll be exactly the same if I put a spring against a brick wall and just one pound block. And somehow this block will go the same speed as the blocks in the other experiment, when no, it's only a one block and all of the spring's motion's going this way. It's not going to go that way. So it's just wrong to say the one mass block won't go twice the velocity, because it will, because it doesn't have another block on the other side of the spring that's moving. Can't you, I mean, to not be able to understand, if this side of the spring doesn't move, then all of the compression energy has to go this way. I mean, duh. I mean, I guess I could draw it. I mean, just say, like, if people can't be this dumb, but apparently, it's just so obvious that here, somewhere in here, if I have these two carts and I have the same spring compression here, right? One mass, they're going to go a velocity, and clearly, if I put if I put the spring on a block that doesn't move, right, then the one mass block has to go twice the velocity. Obviously, it'd be a little less because springs fail. Because springs keep some of their energy; they don't give it all back. But clearly, this velocity is going to be almost 2 velocity, and this velocity is going to be just 1 velocity, and this one's going to be just 1 v. I mean, that's going to be the obvious outcome. That's the intuitive, rational, reasonable, I've lived here long enough to know that's how it works answer. I throw a ball against a brick wall, a rubber ball, I get a lot of the ball's energy back. I throw the rubber ball at, a piece of cardboard. The cardboard moves. The ball ain't coming back. Duh.
Conservation of momentum says that it must be there. It's just so small, no one would ever care, right? So what we're going to do is we're going to draw our little system box around just the crate. We're going to ignore this object. We can treat that as a net force. So that means momentum being transferred from just outside the system, just from somewhere else. So when we started off, the block was at 0 momentum. It's just sitting there. We get it going, we push it, and then we let it come to a stop. At the end, it's once again...
So again, wouldn't it be more reasonable to have the guy push it and the block goes, not the guy and the block?
Again at 0 momentum. So I have moved the crate across the floor.
In amount of time, and the time will tell you how much gravity you overcame.
It started with 0 momentum, it ended with 0 momentum. In the meanwhile, I borrowed a little bit of momentum maybe from the ground object. I transferred some momentum from the ground object up to push on.
So it's just too silly. The ground didn't do any transferring. It didn't give anything, didn't do anything. You worked on both surfaces. You worked on the ground and you worked on the block.
The crate, and then I gave it right back at the end. So that's also 0 net transfer of momentum. There's been no transfer of momentum anywhere.
Right, okay, so a nuclear bomb doesn't transfer momentum to anything. So nothing gets moved, nothing moves, nothing happens. Nuclear bombs go off and it's all like invisible. There's nothing, they're like perfectly harmless. It's just hilarious that people are so upset that the nuclear war might happen because they can't move anything. Why are you worried? It all cancels. Magically.
But I moved the crate. I gave it some momentum, and then it gave it right back. And so we started with zero momentum. We ended with zero momentum.
Oh, it's just too ridiculous. And yeah, what's in the ground? That's the argument. That'll tell you how much work you did. The heat. I mean, it's just ironic, right? I mean, they know Joule, was given a big applause by saying, okay, let's name this energy thing after Joule. And, acknowledging his great contribution. Well, what's his contribution? His perfectly rational statement saying energy is heat. And this asshole is saying, no, it isn't.
And in between, maybe we drug the crate across the floor, and we had to push against.
Drugs is bad, okay? Shouldn't be drugging.
Friction. To do that, maybe we generated some heat, and maybe the heat is actually momentum in the particles in the ground, and that's how we should be looking at this.
Yes. And where are you going to look at it? Are you? Will you look at it?
Maybe we should not be considering that the work we did was a measurable, meaningful quantity.
Oh, so the friction, the heat isn't a measurable or meaningful. Oh, it's just such bullshit.
Let's see if we can use conservation of momentum to investigate these moving blocks. And
so again, it's just all about the friction. By distance, there's no conservation of momentum. Whatever distance would be.
And from that context, can we explain the movement of the blocks purely with momentum? We're going to start with our similar masses. We're going to give them double the velocity. Like the yellow object is going to get double the velocity. And we see that the starting momentum is twice for the yellow object. We launch it, and of course it goes 4 times the distance.
Yes, that's right. And it uses half its energy over 3/4 of the distance. So it's going half its speed here. Here. Not here. Here. So it's going half its speed in a completely non-symmetrical location, which is a huge giveaway that maybe it's not doing the same work during the whole voyage. Maybe it's working harder here than it was working here on the surface.
My understanding is that's not disputed. That's in the original thought experiment. We saw.
So he's pretending he's making a response to an actual argument, and he's just evaded even mentioning it first, even correctly paraphrasing the argument that's being made, which was completely. He was basically saying he was going to ban me, from commenting, because I'm not allowed to talk about weight and friction.
That twice the momentum did 4 times the work. What about going the other way? Let's consider applying some of this work.
So again, we could just put ice here instead of a regular. So this is on a surface of whatever, paper. And then I make this surface ice. All of a sudden the experiment radically changes. And it's not 4 times the distance, it's 400 times the distance. Are we supposed to believe that it did 400 times the work? No, it didn't do 400 times the work. I mean, it's such an obvious way to blow up all this distance crap. You can't sit there and say distance is the work.
Work concept into the blocks and see if we can use that to generate.
Especially when they won't concede that gravity is a time-dependent force. So they're going to say, well, there's 4 units of gravity. 1, 2, 3, 4 in 2 seconds. So gravity is really 9.8 meters per 1/2 second. Yeah, that's the real formula.
Momentum. What if we, instead of just using our springs to just fling these things, let's do some work on the blocks. And
so compressing a spring isn't doing work.
Generate momentum by applying work and see how that comes out.
Oh, bullshit.
So for this thought experiment, let's drop.
Oh, fuck this, right. I mean, now he's got a mystical force that pushes blocks. The mystical, magical pusher of blocks force.
stop the friction. Let's just imagine a frictionless surface. So I've changed it to like an icy blue.
Oh, okay, so if you're going to imagine a frictionless surface, that would be the space analogy. Yeah. Twice the distance, twice the velocity.
It's a zero friction surface. We're going to apply a steady, constant force to our block to accelerate the block. In our previous example, we had half a Newton of friction. This time, we're going to be just pushing on the block with half.
All right, so this is just, I just want to say to the future, do you see this? So not only do these morons who don't know much physics do all of this, just blindly, sheepily defenses of this crap, but you ask these physicists to seriously address a point, and they just won't go anywhere near the subject. They're supposed to have some devotion to this physics being rigorous and true, and you start talking about evidence, and all of a sudden, they're not going to be anywhere near the subject. Because the fact is, they don't have any evidence for this crappy theory. They just keep selling. And there's no, it's snake oil.
Half a Newton to accelerate the block along the ice. How fast will it accelerate? Just a little quick math here using the equation.
So you can't. You're going to make up the friction. You're going to make up how slippery the ice is. Oh, okay. Just make it up.
F equals ma. We can solve that for the acceleration the block will have. And half Newton applied to a 1 kilogram block should result in half a meter per second every second we're pushing.
Oh, every second you're going to do that. So how do you do that? So again, this is just so obvious. It's very difficult to create a constant force. I'm just saying, as the thing keeps increasing its velocity, every little tiny increase in velocity, you have to add more pressure or your acceleration number starts doing this. It's really hard to always be applying the same acceleration. Gravity does it because it's a speed of light force that goes through every bit of your body. I mean, it's a completely different mechanism. We don't have any such mechanism here on Earth. Oh, these people are such frauds. Ugh, it's disgusting.
On the block. So if we push on it for 1 second, we should get it up to half a meter per second. If we push it for 2 seconds, that should accelerate the block up to 1 meter per second. Okay, that seems pretty straightforward. In that amount of time, the block is going.
It doesn't straightforward at all, right? Because they're just basically saying, I'm going to keep increasing the acceleration. I'm going to keep running faster and faster and faster and faster as I push just five units of energy faster than I'm running. I mean, it's an impossible task.
Going to cover 1 meter. And I'm not showing the math for that particular piece of the puzzle. If you need to see that, let me know, and I'll show you how we.
Oh, wait, bullshit. Jesus Christ. It's such an evasion.
You can get that. Okay, so the block is now moved a meter, and we're going to let go. We're going to stop pushing. But the block is not going to stop because it's on that frictionless surface, right? No more friction in this example. So we've left the block at 1.
Yeah, so what's the point of this argument? Because it can only go twice the velocity is twice the distance in a unit of time. And it's going to keep going. So it's any unit of time, it's going to be twice the distance of using a 2 kilogram block.
1 meter per second. And that is the equivalent of 1 kilogram meter per second of momentum. And a kilogram meter per second can be called a Newton second. So we've got 1 Newton second of momentum. How much work did we do to get us here? We did half a Newton of force, and we put.
It's just too ridiculous. This has nothing to do with the subject, obviously.
For 1 meter. So that's half a Newton meter of work. Maybe that's just a consistent conversion, right? Maybe just every half Newton meter of work you apply, you get another Newton second of momentum. Let's look at that. Let's consider pushing for twice as long. We're going to do the same exact half a Newton, same exact 1 kilogram. And this time we're going to push for 4 seconds. We're going to push for twice as long. In 4 seconds, we're going to get that brick up to 2 meters per second, twice as fast. Push twice as long, you get twice as fast. In that time, we're going to cover 4 meters.
Yeah, so there's no evidence you're going to do 4 meters, blah, 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 blah. But even so, it doesn't matter. You know that once you let go, you're not going to do 4 meters. In no friction, again, there's no way you're going to do 4 meters of distance when, 4 times the distance if there's no friction. I mean, again, he's saying pushing something twice the velocity, somehow it goes 4 times as far when there's no friction. In space, I push it with twice the force. He's saying that somehow he knows it takes you 4 units of distance to apply twice the force. It doesn't take you 4 units of distance.
Meters. Not 2 meters, but 4. Now, why is that?
It's the same, if it exists, it's the same reason that gravity does it. But again, we're not in gravity. Let's see, is there any point in making an argument? So look, as I pointed out, we can't even create this force. And yes, if you're going to make the argument, then the same argument would be true for paint spray and all these other things that behave exactly the same way. So if you're going to just sit there and incrementally imagine how much your velocity increases, fine. But once you have the velocity, it's not going to be 4 times the distance anymore. You're just going twice the distance. So he's just playing a game with the idea of the initial transfer of the energy, and saying the initial transfer of the energy defines how far it'll go, and it doesn't. Now in gravity it does, because it keeps going 1, 3, 5, 7, 9, because it keeps gaining more and more velocity. But he already established he stopped pushing. So we know once he stops pushing, twice the velocity will be twice the distance. So this is just such a distortion. Oh, he's such a cheater.
In the first 2 seconds, we covered 1 meter. But at the end of that time period, the block was already up and going now. It's already going 1 meter per second. So in the next 2 seconds, with the block already off to a good start, we're going to cover distance much more quickly.
All right, so the argument is it's not 4 seconds, right? Because we know in gravity it's only 2 seconds to get twice the velocity. So he misspoke saying it's 4 seconds. It won't take 4 seconds. It'll only take 2 seconds. It's only going to be 2 units of force, and it's only going to be in 2 units of time.
So we're covering a lot more distance with the second half of the push. When we're done, we will leave the block sliding along on our frictionless surface at 2 meters per second. We did half a Newton times 4 meters, or 2 Newton meters of work. So that's 4 times the work.
All right, so he keeps saying it's 4 times the work. And in this case, there's not supposed to be anything, that you're doing work against except the object. So, but obviously that doesn't matter because you only have twice the velocity. So right after you stop pushing, there's no evidence there's 4 times the energy in the object, because it won't be traveling 4 times the distance anymore. It's just such a cheater.
But we only got twice the momentum. Let's look at this broken down in a little chart here. I've got it broken down a second at a time, and we're going to look at halfway through. At halfway through our little slide, we've been pushing for 2 seconds, and we've built up 1 Newton second of momentum. And then in our second half of the push, we've been pushing for 4 seconds now, and we built up twice as much, 2 times the momentum. But it's 4 times the work. Now look at this. This is half, and this is 2.
So again, he's saying it's 4 times the work, and there's no friction, there's no force opposing. So obviously, why would you think it was 4 times the work? So again, you're dropping something in gravity. In the first 1/4 of the trip, it's going half the velocity. So in this small distance, you do 4.8 meters in 1 second. And then in the next second, the next 1 second, you're going to do 3 more of those. Obviously, 2 of them you get for free because of the 9.8 increase in your velocity, and the other one is the 1. You just get 1 more unit, 1 more unit, 1 more unit. But your velocity keeps accruing, so you're going to travel more distance because you have acquired an accrued velocity. I mean, it's just, it's just ridiculous for you people to actually think twice the velocity is 4 times the energy. It's just silly.
2 is 4 times the amount of work.
It isn't.
And I think there's a case to be made there.
2 units of time, 2 units of velocity. No good reason to intuitively think that's 4 times the work. You were in the paint spray twice as long. Why would somebody think you have 4 times the paint on you? You were in the stream twice as long. Why would somebody think you have 4 times the deflection? Why?
That only twice the momentum doesn't make sense that we would call that 4 times the work. It doesn't seem reasonable. Why are we squaring? Why are we
There you go. That's the essential question. So we would have to wait through this whole video to get to the essential question. Why the hell would we think so? And what did Leibniz prove it with? Did he have an experiment? No. He had the claim that 2 things with completely different momentums, that is, one thing has twice as much momentum, will do the same work. So even though I have twice the amount of momentum, I'm going to get the same work out of it. That's not intuitive. It's not reasonable.
squaring that? Why are we squaring the velocity?
Yes, why? Why are you doing this stupid-ass, retarded, silly fucking thing? You don't square the voltage.
Ultimately, what's happening is the velocity is being squared there, right? Why is that? Why is that? It doesn't make sense. This should be what we call a doubling. This is the work we did, not this. This is a nonsense number. But let's consider it again from how much effort we actually had to put in. When we started...
2 units of force. It's only 2 seconds worth of pushing. As you're increasing the velocity, you're covering more distance in less time. As you increase the velocity, you cover more distance in less time. It's only 2 units of force, not 4 units of force. You're pushing in units of time. God damn it.
With our push, the object was at rest. You're standing on the ground and you push with half a newton. As you push, the object starts to accelerate. In our second half, we're still having to generate half a newton of force, but
It's too bad he just doesn't do the 2 examples and just show that, no, it's only twice the amount of time. You're only pushing twice as long. Not 4 times as long, just twice as long. You're pushing with the same amount of effort for twice the amount of time, and he says that's 4 times the work and 4 times the energy. Obviously, stupid.
have to do it while the crate is moving at 1 meter per second already. That means we have to kind of jog along with the crate while we're pushing. And it just keeps getting worse and worse. As we keep pushing, the crate keeps going faster and faster and faster. So it's not enough simply that we are pushing for 2 seconds per block here. We're pushing for 2 seconds while we're running along with the crate.
It's not about you running along. It's about how much force you're applying to the crate. So again, it's completely wrong to say you're doing an experiment with this pusher having momentum, and you're going to worry about how much work it takes to give the pusher momentum. Well, again, that's like saying, okay, levers, they have a weight, a mass. You have to subtract that from the experiment. You can say the carts in experiments have masses. You got to subtract that from the experiment. The angular rotation. This is all just simple logic to say it's not about how much work you're doing to get your body to go. It's about how much work you have to do to get it to move. How much are you giving to the block? It's not about how much work you did to push it, because frankly, you're not a spring. You didn't use the example of a net force, where you coiled your body up and then you pushed. That would have been a much better example, because then all of this crap about how much work you did wouldn't matter.
It's kind of like trying to push against something while you're running on a treadmill. Perhaps that gives you a little bit of an intuitive feel for why it is more work.
Okay, so it's not more work, it's just 2 units of applying the same force. 2 units of applying the same force is not 4 times the energy. Too silly, too stupid.
To push on something that is already moving than it would be to push on something that is at a standstill.
Yeah, obviously something that it'd be really hard for us to go as fast as a bullet and push the bullet faster. Yeah, because we're a big giant thing. So yeah, it would take an insane amount of energy to get us up to the speed of the bullet, and then we have to just flick the bullet like that to add the extra energy. Yeah. So what? What does that have to do with the subject? I mean, it has nothing to do with the subject. Obviously, you could push the thing with a much more discrete force. Not a big human, but you could push it with wind, or you could push it with, a discretely tiny gravitational force. And then all of a sudden, you're not going to be doing all that much work. Even if you use the sandblaster example, let's say you had the sandblaster produces sand moving 500 miles an hour. Obviously, you only need a tiny number of those things to hit to give you the momentum. So you're not going to have to, the sandblaster, the pieces of sand aren't going to have to do a whole lot more work to push something 1 mile an hour to 2 miles an hour. They're already moving 500. I mean, you just don't get energy in the universe at all. You people are just so fucking delusional.
And that still seems kind of wrong to you. The idea of having to run along with something while you're pushing on it, adding up to extra work, if that doesn't seem intuitive.
It's not how a stream works. It's not how paint works. It's not how any of the forces that we can compare gravity to work. So again, it's just playing games again, just trying to pretend that there's some problem and we have to do more work. No, none of that happens in the real world.
To you, maybe go and look up acceleration curve.
Oh, go fuck yourself. Go look up head in ass.
For cars. Notice that the acceleration curve for a car shows the car can accelerate much more rapidly at a standstill or at a slow speed than it can at a higher speed.
Yeah, much more? So where did you get this from too? Yeah, why don't you show us? Why are you saying look it up? Why don't you just show us these dramatic numbers? You have to come up with 25 times the fucking force. 25 times. Not 0.28 increase. 25. Oh, you're such a weasel.
And part of that is, of course, from aerodynamic drag, but a major contributor to that effect is the fact that the car is already up and moving, like in this example. The car's already up and going, applying a...
No, the real point is that it's going across a surface where it's applying less and less contact force. There's less and less contact force with the surface. Duh.
Additional force to it means that engine has to rev up to match the car's current speed.
Okay, so none of this, again, he's just making this stuff up. There's no 25 times the engine revving to go 5 times as fast. None of that happens.
And then continue pushing harder. That's even true for electric cars. Of course, it's...
Liar, 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 liar. It's just a lie. I mean, it really just has to do with the wheels. So frankly, the whole thing, this whole subject would be moot if you make the wheels out of like, tongue and groove, and with the ground. So there's a real solid whack contact, like a water wheel. A lot less waste then. So you can't use silly arguments like this then.
It's true for electric cars, which are even simpler. We won't have to deal with changing gear ratios or anything. Most electric motors in electric cars are capable of generating consistent levels of torque, which is the equivalent to force in this example. And the consistent level of force that the car can put down reduces the rate of acceleration the faster the car goes.
All right, so this is bullshit. Of course, the motor has to spin faster if you don't have a gear ratio. So if you don't use a transmission, it gets less and less efficient. Everybody knows you try to go 50 miles an hour in first gear, you're going to have a damn tough time.
And that's because of this exact phenomenon here.
There's no exact phenomenon. Oh, this is just such a lie, such a deception. Produced zero statistical or any kind of evidence whatsoever to demonstrate this happens. This is all so fucking bogus.
Car is already up and running. It has to sort of chase itself down. It has to keep running with itself while it's pushing. And that takes extra effort.
So again, lie.
Coasting does not take any effort, right? You can just put the car neutral and you can coast. No effort required.
Right, so that's the whole point that's being made, right? You're coasting, and now you want to go a little bit faster. You just apply the same energy you applied to get the first 5 miles an hour. The 15th 5 mile an hour increase is going to be the same energy, just like pushing on a spring is going to be the same energy. This 1 pound on the scale is going to take as much work as 2 pounds on the scale. It's going to take as much work as 3 pounds on the scale. It's going to take as much work as 4 pounds on the scale. It's all the same work to compress the spring. So you people are just so full of crap.
But if you want to accelerate, you'll have to apply that force, and that means you're going to have to run along with the object.
Again, just nonsense. The forces do not run along with the object. A force going the speed of light is not going to have any relativity problem pushing. Yeah, 1 mile an hour objects.
And push on it. Okay, let's take a pin in that one. We'll come back next time and try to explore coming at this from strictly a momentum point of view.
He keeps saying it's strictly from a momentum point of view. The evidence is supposed to be the point of view. Momentum works. You don't need to prove momentum works or try to disprove it works, because it does work. So there's no argument that momentum isn't conserved. The argument is there any such evidence that any of this v squared energy, the scalar crap, this mystical scalar energy, woo 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 woo, the Holy Ghost energy, that does any fucking work in the world? That's the one you're supposed to show. Show us where it does actual work. Collect the work somewhere. You can't collect it with a ballistic pendulum. You can't collect it with a rocket ship. You can't collect it with a garden hose. You can't collect it. I mean, I could go on and on. You can't collect it with any experiment. Can't collect it with crashing cars. Can't collect it with anything. It fails every time to do any work. And here you are selling that crap. Disgusting. All right, well, made it through the video anyway. I don't like having a condition for which I don't understand what the fuck it is. It's just so strange. But anyway, I mean, I thought I might have had Lyme disease again, but I don't have a temperature. Well, I don't have a consistent temperature. But man, I was just, I'm better, but I'm not, I'm not as bad as I was, but it's just, yeah. Anyway, till the next time and such.